Okay, so let's continue. This is the part 2 of the video. So those who are not seeing the part 1, I request you to see part 1 first, and this is the continuation. So this was the system for which we try to solve the load flow problem. And here I have the 2 bus system, bus 1, bus 2, and then the Y bus, and so on. So we had written down the power flow equations. Then specifically for a 2 bus system case, I have written down once again the P2 and Q2 equations. Then from that I formed 2 functions, FP2 and FQ2, and these 2 functions are equal to 0, and then I have written down these functions here. From that I have formulated the Jacobian matrix where I take the partial derivatives. So the 2 functions are, so here I'll write 2 functions are fp2 and fq2, and then 2 unknowns, they are delta 2 and v2. So the ordering should be first the deltas should be ordered and then followed by the v's. Similarly here the first p's should be ordered followed by the q's, and the delta corresponds to the p and v corresponds to the q. So uh, that is the understanding that we have. So continuing, so I have, since 2 unknowns and 2 functions, so I get 2 by 2 matrix, and I take the first function, differentiate it with first unknown. Again the first function differentiate with the second unknown, and the second function differentiate with the first unknown, second function derived with the second unknown, and so on. So I once again replicated the 2 functions, and then their differentiation is here. Once I have these two, then I can use the last equation here for running Newton-Raphson load flow. So let me now define these functions. So I'll go to my MATLAB interface. So here on the left side you find a new program. So if I just execute this, is just clear all and clearing screen. So I'll begin by displaying the title of 2-bus system. So we start by defining the variables. So I already have Y bus. So I can actually define it as a 2 by 2 matrix, but then because it's easier to name the variables, I'll just write it like this. So capital Y1, capital Y12, so Y21 and Y22. So these are the 4 elements of the Y bus matrix. So Y11 is the first row, first element, first row, second element, and so on. So if I go to my solution, so if I go to the top, so this is the Y bus. So minus J20. So here I'm only interested in magnitude. So you see all the elements are 20, 20, 20, 20. So everything is 20. So 20, 20, 20, 20. So you might say, what about the sign? So some are plus and some are minus. So for example, so here the sign represents the angle or phase. So I consider it as minus j into 20, plus j into 20, and so on. So minus j means minus pi by 2, and j means pi by 2 as our angle. So that's what I'll define here. T12, this is theta actually. So T12, sorry, T11, T12, T21, and then T22. So these are my thetas, the angle of the Y bus. So you notice that the diagonal elements are minus pi by 2 and off diagonal elements are pi by 2. So I have to define the angles in radians. So minus pi by 2, and the last one is also minus pi by 2, whereas the other 2 elements are pi by 2 and pi by 2. This is pi. So I have defined the Y bus. So let me give the title here. Defining the magnitude and angle theta of the Y bus elements. Okay, that is done. Now I also have the known variables. So that is V1 equal to defining the known states of the system. So state means the voltages. So V1 I know that is 1 per unit. Just a minute, I'll come back. So V1 is 1 per unit, and then D1 is 0. So V1 D1 is the voltage and angle of the first bus. Now what are the unknowns? So here I'll write initializing the unknowns. So what are my unknowns? So V2 is unknown. So I'll consider it as this one. But then again remember the ordering of the unknowns, D2 equal to 0. So in fact to save space you can define like this. So yeah, so I have defined two variables here. Now what is the next step? The next step also I have some known quantities, that is the P2, the power injected at bus 2. So if I go back to my system, here you see 1 per unit and J 0.5 per unit. So that is actually the demand. So but then here I want to define the power injected, so it will be minus 1.0. So why I am taking the negative sign is in the equations Pk represents the net power injected into bus K. So but if it is a load, then I have to take the negative of that. Similarly Q2 equal to minus 0.5. So this is about P2 and Q2, the net power injected at bus 2. So these were also knowns. Now once I initialize the unknowns, the next step is I set up the Newton-Raphson iteration. So for that simple, I create a dummy variable m equal to 1 to 5 and then end. So let's imagine that I'm running the for loop 5 times. So that's why for loop is there. So whatever I specify in these lines will repeat 5 times. Okay, so what are the things I would like to specify? So if I go down to the last section, what I have done, I have the function values fp2 and fq2. These two function values I'll define here. So fp2 equal to and then fq2 equal to. So these two functions I already written down, y21 v1 v2. So let me write that y21 into v1 into v2. Then cos of theta 21 plus delta 1 minus delta 2. So into cos of theta 21 plus delta 1 minus delta 2. So this is the first term of the, I think this itself is the first term. Of course minus P2 is at the end. So what about the second equation? The second equation is minus of everything. Just replace this theta 21 by cos by sine, and then there's one more term. So let me just copy this up to here. So here I put a minus sign, and then this cos I'll replace with sine. So this is one term. Then the other term is plus y22 v2 square. So plus y22 into v2 square. Then I have minus q2 at the end. So minus q2 at the end. So this is the equation for fq2. Now I want to define the Jacobian matrix. So I have 4 equations written for Jacobian matrix. This is J11, J12 and so on. So I'll write that J11 equal to J12 equal to J21 equal to and then J22 equal to. So since I derived these expressions, I'll just write them now. So this one is very similar to this. So I'll just copy this. Now you might get a doubt how these things are, from where these equations are coming into picture. So again, as I said, see my previous video. Then this is a continuation video. So you, in the previous video, I have derived this. So this term I have given y21 v1 v2 sine theta 21 plus d1 minus d2. This is done. Next one is this one. So j12. So y21 v1 cos of y21 into v1 into cos of theta 21 plus delta 1 minus, okay, t21 plus d1 minus d2. Okay, so this is my equation. Let me make it a little bit more compact. Although it appears complicated, it's not actually complicated. If you know what you're doing, it is basically straightforward. So it's not that difficult. Now let's do J21 term. So J21 is this one, y21 v1 v2 cos of all of this. So I think this itself, except v2. So v2, I have to remove it. No, I think v2 will be here. y21 v1, okay. Now here, this one, so I just take this entire thing and then differentiate it with v2. So that means v2 will be not there, and then here 2 into v2. So this is my fourth term of the Jacobian. Finally, I can form my Jacobian matrix just by taking J11, J12 in the first row, followed by J21, J22 in the second row. So this completes my J matrix. So I have done this. So this one I have done, and this one I have done, and all the 4 elements I have done. So the next step to program is this one. So the new value of the unknowns is nothing but the old value of unknown minus this. So let me do that. So my unknowns are d2, v2. So here I am initializing the unknowns, but then let me call the entire unknowns as capital X. So capital X is nothing but d2, v2. I'll just define it as a column matrix. So capital X equal to capital X minus the function value. So the function value I'll define as this one. So I use this operator, J backslash, and then the function values, fp2, fq2. So this is this function backslash in MATLAB. It calculates the inverse of the J matrix and then multiplies it with this. So pre-multiplies with this particular vector. So this is what exactly we had derived in the formula. So my X value will be updated. So here, let me update the variables also. So although I change the value of X, the D2 and V2 values I need to change. So D2 is nothing but the first element of X, and V2 is nothing but the second element of X. So I have updated the values. So let me give some comments. So calculation of function values, calculation of Jacobian elements. Okay, so this is calculation of Jacobian elements. And then finally here, updation of unknown variables. So, and this process I'll repeat it 5 times. So once this process is repeated 5 times, every time I repeat it, I want to display on the screen. So let me display capital X transpose. So it will horizontally, it will display the values of X. So if I have done everything correctly without any mistakes and all, hopefully I'll be able to solve the load flow problem. So let me run this code now. Yes, so on the right side, So I'm able to see some result. So this one I'll comment it out so that I don't display that. And then here I'll say disp, because I don't want, just only cosmetic improvements I'm doing it. So these are the, on the right side you see, these are the results. So 972985 is the voltage magnitude of bus 2, and then this is the delta 2 expressed in radians. So delta 2 is expected to come in negative because this is the receiving, so the slack bus should send the power to this, so the delta should be less than 0, so that's why it is negative. But this is in radians, so let's display. uh, so so disp final value of V2 delta 2. This is just a text I'm displaying. So here I'll display. First is I want to display the magnitude of V2. So x of 2, or I'll simply say V2. And then delta 2 I want to convert into degrees. So 180 by pi. So this will be my final solution. So some syntax error maybe. Yeah, the closing bracket I forgot. So final value of V2 voltage is 97298 and then minus 2.9453 degrees. So let me write this in the solution. So final solution via MATLAB code. So I get is V2 delta 2 is equal to 0.972. I'll just approximate to 973 at an angle of minus 2.945 degrees. So this is the final solution. If you recall, we had similar solution using Gauss serial load flow method also. So with this, I had solved the two-bus system of the Newton-Raphson load flow. So those who are seeing this video on YouTube, I will also provide you the link to download the MATLAB code for this. So please do that. And you can download the MATLAB code, you can study it and you can run it and then check it. So in my next video, I'd like to solve slightly bigger problem with 3 variables and then we'll see how it works. Thank you.